let's talk about a few things today. So the first is going to be standing waves. Let's talk standing waves. There we go. And the implications of standing waves. So first things first, I think maybe the best example of a standing wave is a spring or a string with fixed ends. Okay, so fixed between 2 points. And if we were to pluck this string, what we would find is that a standing wave oscillating with 2 points of destructive interference at each end, so no amplitude, okay, here, would be set up, okay? And in the middle, you'd have a large amplitude. So just in terms of defining the parts of this, okay, places where you have no amplitude, we call those nodes, okay? So the first question is, why does this happen? Why do we get this shape, okay? You can also do this just by having 2 people hold onto a slinky at either end and wave the slinky up and down. You get an oscillation like this, and you'll get these 2 nodes at either end. So this is a consequence of the idea that if you have a medium that's fixed at one end, in this case fixed at both ends, and you send a wave down, well, the wave that comes back off or reflects off of this end is inverted, okay? Now, if you send multiple waves down, okay, well, what happens is an inversion of that can come back the other way, and you end up with interference zones, okay? And that's kind of the basic concept. It's that incoming waves are interfering with their reflections, okay? So what we'll do, and as you increase frequency, remember, right? As frequency increases, so as frequency goes up, wavelength goes down. This is making the assumption that the wave velocity is held constant in that medium, right? So as you have a higher frequency, that means more waves are hitting in a given amount of time. If they're traveling the same speed, well, that must mean that they're shorter, right? Kind of stands to reason. All right. So we're going to imagine then that you have this string set up. So I'll set it up here. You pluck it or wave it, and you get this kind of a standing wave set up here. In the world of standing waves, this is called the fundamental. Okay? And the frequency associated with it, whatever frequency this is vibrating at, it's called the fundamental frequency. And this also has another name in music. The tone that a string would make that's doing this would be called the first harmonic. Okay, so the fundamental frequency or the first harmonic. Okay, so we have this string right here. Now, what can we say about this? Well, if you look, there's exactly half a wavelength standing in this string, right? If we continue it out to here, we see, okay, now we've got a full wavelength. So if the string length is the distance between the 2 ends, okay, for the first harmonic, we could say this. The wavelength is equal to 2 times the length. Or the other way around, the length here is equal to 1/2 of a wavelength, okay? So this is kind of the basic math behind this, all right? Now you can obviously crunch numbers with this, but to me, it's really just important that you understand these relationships and you can kind of figure them out for yourself. When you figure them out for yourself, everything else will come easy. Okay, so now, if we increase frequency, we're going to shorten wavelengths until eventually we hit upon another frequency where you can get this standing wave that'll sit and create this kind of a pattern. Okay, so it looks like this. So what's going on here is basically here's your string, and it's just oscillating up and down like this, okay? And you have now got 3 nodes, right? So you've got N, N, and N, and you've got 2 antinodes, okay? This is called the second harmonic, sometimes called the first overtone. I know there's lots of names for these because some comes from music and some comes from physics. And secondary standing wave. is another name for it. And you might hear some others just depending on who you're listening to, but you can usually figure out what they're talking about. Okay, so remember, you still have the same length, you still have the same tension in here, so therefore the wave speed is the same. Okay, but now you're going to have basically a higher frequency here, and if you double the frequency, you have the wavelength. So essentially, you would get this at 2 times the frequency that you got this at. Okay, so there's this mathematical kind of relationship, and now you've got this length is equal to 1 wavelength. So there's your 1 wavelength, or wavelength is equal to L. Okay, and you can keep going with this. So you can get another one if you increase frequency even more. It comes like this: tertiary standing wave, third harmonic, whatever you want to call it. Okay, and now what you have is you have 1.5 wavelengths is equal to L. Okay, or a wavelength, 2/3 of this is 1 wavelength, so 2/3 of L equals a wavelength. Okay, now remembering that the velocity is the same, if you decrease the wavelength, you could probably figure out that there is a mathematical relationship between these frequencies, and you can figure out what frequency that happens at. Okay, and I'm just going to give you an etc. Okay, so I'm going to give you an etc. because this same concept just continues on, right? The next one comes at 2 wavelengths. Actually, maybe we'll draw 2 wavelengths just before we quit. Okay, 1, 2. Get this kind of an oscillation. So now you've got 1, 2, 3, 4 antinodes, and you've got 5 nodes. Note you always have one more node than antinodes, and the order of the standing wave. So 4 prime, or not 4 prime, 4 naught order, 4th order standing wave, I guess you could call that, or 4th harmonic. Okay, or 3rd overtones, depending on what nomenclature you're using. We'll have 5 nodes and 4 antinodes. So I just wanted to finish up with a couple of nice little GIFs, one by Dan Russell, one general one that I found on the net. So what you got here is you have your green reflected wave interfering with your blue, say, input wave, and then you get your standing wave looking like this. Now, in this, we would have our nodes here. So this would be an antinode, antinode, and antinode. So this is a 3rd order, of course, ignoring this. Okay. Now you can also get standing waves in with sound. So if you have a tube that's open at one end, you can get a standing wave in there that looks like this. Now, realizing that sound waves are longitudinal, we're going to just represent it as a transverse wave. So you can have a tube closed at one end. So this would be like your classic beer bottle that you're blowing over the end of, and it's making that like that low toned humming sound. And if you increase the frequency, you would get the next standing wave in that bottle and so on up. Let me get my pen to work here. So you'd get one that's like that. Okay. So here you have an L that's equal to 1/4 of a wavelength. Here you have an L that's equal to 3/4 of a wavelength. Your next one will come at 1 1/4, 1 3/4, and so on. Okay. So this is represented here. You notice you have a node at the end. Okay. You have a node at the end. Node, 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 node. You've got an antinode, 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 and then you have to have an antinode at the opening. So that's this, because you got to be able to send this out into the air. You wouldn't be able to hear it if you didn't have it out into the air. Okay. So this would be the, so this is the first. Okay, so you got 1, 2, 2 1/4 wavelengths. So 2 1/4. So 1st, 2nd, 3rd, 4th, be at 1 3/4, and then, you know, the 6th, I guess, I think. Anyway, it's applicable when you're talking about musical instruments. So let's say you had something like, I think an oboe might work like this. I'm not exactly sure, but you blow in, okay, a vibration gets set up here. That transfers into the air inside of here, and you get any order of standing wave depending on, and mostly what you'd hear would be the fundamental, depending on where you're fingering or changing the lengths of this tube. And we'll end it there. So just look at this one more time. Okay, so a longitudinal wave has points where there is no motion, so a node, and points where there's lots of motion, so an antinode. In order to hear it, you have to have an antinode at the opening. You can also have tubes that are open at both ends. So like I don't know, like maybe a recorder or something like that. Okay, so you get a standing wave in there that looks like this. That's a half wavelength. Doesn't maybe look like one, but it is. Okay, and then your next one would come there. You have a whole wavelength, etc. So that's with sound, okay, closed and open tubes, and with strings.